Can we start?
Okay, so let me first wish you a wonderful 2017, and this is the first colloquium tour for the year. And as you know, we are going to also to restore this room in the next weeks. So this is the last in the old our path, and then we will make the next one in the new setting. Let me thank also Fabio for organizing the colloquium talks and the recordings that will be posted on our website as well as YouTube and advertised on Facebook and so on. The colloquium talk of today will be by Renato Calleja, who is an old friend of mine, and I'm very glad that he's here this week. Let me tell you something about Renato. He's from the Departamento of Mathematics and Physics of the Universidad Nacional Autónoma de Mexico, UNAM. He had his bachelor degree in Mexico, and then he moved to Austin, Texas, where he obtained his PhD in 2009 with Rafael de la Llave. Then he had several postdoc positions and visiting positions. Let me mention some: McGill University in Montreal, Canada, then the Institute for Mathematics and its Applications in Minneapolis, the University of Minnesota, visiting assistant at Georgia Tech, recently visiting professor in Barcelona, then visiting professor again in Montreal, and since 2013 he is a research assistant professor at UNAM in Mexico City. The scientific results of Renato cover different fields, which range from dynamical systems to analysis, and in particular KM theory for symplectic and for dissipative systems, which is the topic of the talk today, numerical methods for the computation of the breakdown threshold. Then we are also explicit estimates in KM theory. Let me say that he has an excellent skill in mastering very complicated computer languages, programming languages. He also has results about periodic solutions of delay differential equations, response solutions for wave equations, and more recently, this morning, he showed me very nice results about a new topic that he is facing in the last months, which are choreographies in celestial mechanics. So that is very special configurations in celestial mechanics. Let me say that I've always been impressed by the talents of Renato, both in mastering analytical and computational aspects in analysis and dynamical systems. So it is my great pleasure to welcome him in Roma and to introduce his talk, whose title is Quasi-periodic Solutions in Conformally Symplectic Systems.
Thank you very much for the very nice introduction. I mean, I'm a little bit embarrassed by all the things that have been said, but I'm always happy to come to Rome. I've been here several times, and of course there's excellent people here. I always have a great time discussing mathematics, and of course not only the joint projects that I have with Alexandra. So let me talk about one of them. So I've been also told that the audience is a little bit broad, but I hope everybody will find something interesting here. I promise to show a little bit of analysis, functional analysis, complex analysis, dynamical analysis, and of course numerics, and also geometry. Okay, so I hope this is broad enough so that everybody finds something interesting. At the same time, I see a lot of very good experts in the topic, so I hope so the experts also find something interesting here, and I will try to be a little bit broad. Okay, so I will talk about quasi-periodic solutions. So this is related to KM theory. in a very special kind of systems which are conformally symplectic, which is already a geometric definition of a dynamical system, and I will specify that in a minute. And of course, there have been many people, I mean, we've been following this project for a number of years. I started with Alessandra and Rafael back in 2008 in a meeting in Barcelona. So there have been many people involved. Let me write some of the names. So of course, this is joint work with Alessandra. And then Rafael de la Llave. And there have been other contributions with other people. I see here, for instance, Corrado. So, Fattorini. I will mention also some results that I got with Jordi Luis Figueras from Uppsala University. And well, I don't know what else to. I will mention also the work of my master student, Adrián Bustamante. And I'm probably forgetting something. I mean, now that the project has evolved into involving other different people, so I recently started working with Alejandro Alexaro and Marta Canadei from the University of Barcelona. So I will unfortunately not be able to cover all the results that we've completed together with all of these people. I'm probably forgetting some people, but in the slides I will specify what were the results and the people that were involved. So so let me start by presenting my plan. So first I want to introduce what are conformally symplectic systems from the point of view of geometry. These are dynamical systems that satisfy a very specific, geometrical characteristic. Okay, and I will focus on KM theory. So that is the existence and persistence of quasi-periodic solutions for this kind of system. So I will present briefly some kind of theorems and what we use these theorems for. In particular, we're going to use these theorems to describe quasi-periodic solutions that live on smooth manifolds, that is smooth chloride, analytic chloride. And I want to study also the transition of this chloride from smoothness to non-smoothness. And there are some recent results that will be involved. I will mention that during the talk. And at the end, I will say some things about something that we've been doing more recently, which is the limit of small dissipation. Of course, these conformally symplectic systems in many cases are dissipated systems, a very special kind, a small group of dissipated systems. And lately we've been studying what happens to these quasi-periodic solutions, to this chloride, as the dissipation goes to zero. Okay, so let me start by mentioning a little bit of, well, I mean, these systems from the point of view of where the systems show up. Of course, these systems have been studied for a long time in the context of non-equilibrium statistical mechanics and transport theory. So there's the work of Deadman, Morris, Perangelo Librani, who's here, and Wolkowski. And of course, I got interested in these systems from problems in celestial mechanics that I will briefly introduce right away. And of course, there are systems in celestial mechanics where you have forces, dissipated forces present, and the forces happen to be very small. And in many cases, those systems are also conformally symplectic. And the reason why is that any Hamiltonian with a friction that is proportional to the velocity is a conformally symplectic system. So this is okay, I said that this was a very small set of dissipated systems, but in some sense, in the context of applications, this is a very natural geometric setting, because modeling the friction as something that is proportional to the velocity is a very natural assumption.
So that's true in any dimension?
Sorry?
It's true in any dimension?
In any dimension, yes. It is true in any dimension as long as the dissipation is constant, right? The symplectic factor is constant. Okay, I will say something about that. In dimension 1, I mean 1 degree of freedom, you could have a dissipation that is non-constant, but that's pretty much how far you can go with a non-constant dissipation. Okay, so this is the geometrical setting. Let me start talking about a conformally symplectic flow. So I start with a symplectic form, omega, okay, on a symplectic manifold, and I will say that a conformally symplectic flow is such that the derivative of the symplectic form in the direction of this vector field x is equal to a, well, I put here a function, later I will make it a constant, eta times the symplectic form. Okay? As I was just mentioning, in general you could assume that this eta is a function, but in order for to have a conformally symplectic system, you need a dimension of the degrees of freedom to be equal to 1, or n equal to 1, as I'm stating it there. Okay, so what does this mean in terms of the flow, the time t flow of the system? If you have a conformally symplectic vector field, then the time t flow has to satisfy that relation here at the bottom. So the pullback of the symplectic form via this map, time t map, is equal to a constant times the symplectic form. So this is the geometric setting. That's what the flow is doing to the symplectic let's say quantity. It's contracting it with this rate. So now that I've introduced that geometric setting, let me introduce a conformally symplectic map. I will just take a conformally symplectic map with that definition. I take the symplectic form, if I take the pullback via the conformally symplectic map, I get back the symplectic form times a factor lambda. And going back to the question, throughout this talk, I will always assume that lambda is constant, right? Of course, it could be a function in the same in the case of n equal to 1, but and that is something to explore. But for now, I will assume that it's constant. Okay. So this was kind of the first example that I was introduced by. It was introduced by Alessandra to me. So it's a displaced spin orbit problem. So it's basically a problem from celestial mechanics, and it involves a two-body problem, a Eulerian two-body problem, where you have two primaries. One of them is at the focus of an ellipse, and the other one is moving along an elliptic Keplerian orbit. And so it is a spin orbit problem because you assume that the body that's at the Keplerian orbit is rotating. Okay, it's rotating in well, it's rotating with an axis that is orthogonal to the plane of the eclectic. Okay, so that is the spin orbit problem, and moreover, it becomes dissipated if you assume that there's frictional forces that are due to tidal torques. Okay, so this term that I showed here is modeling a tidal torque. It's an average tidal torque, but it's that term is due to the fact that there's the torque it introduces some friction because the planet is not rigid but is quasi-rigid, and it presents some resistance to rotating. Of course, the model is such that, well, x is going to be that angle here. That's the orientation of the satellite there. So x satisfies that differential equation, and of course epsilon depends on the moments of inertia of the satellite along the eclectic. Okay, so what do we have here? Of course, there are basically two relevant angles here. One would be related to the true anomaly along the Keplerian orbit, and the other would be the orientation of the satellite. Okay, so I could take these two angles on the torus, And of course, I could have here I could have periodic or quasi-periodic orbits. For instance, if I draw an orbit on this torus, I have a representation of the torus here on the square. If that trajectory on the torus closes up, okay, then I have a periodic orbit that amounts to omega 1 over omega 2 equal to omega, and omega is rational, right? That is the case of the moon. For instance, the case of the moon, we always see that the moon always shows the same phase towards the Earth. So that means that that would be a periodic orbit of with omega equal to 1, right? Because the moon always comes back with the same phase. So what does it mean to have a quasi-periodic orbit? Well, so let's see what happens when omega is irrational. First of all, if omega is irrational and I just draw a linear flow, I know that the linear flow is going to cover densely these two torus. Okay? So what does that mean on this caricature of the spin orbit problem for our model? So the model being quasi-periodic means that the planet here on the Perpetual orbit is never gonna come back to the same place, showing exactly the same phase. But the phase is gonna be always different, and eventually the phase can come very close to the first that we saw in the beginning, but it's never gonna be exactly the same. So that's why this trajectory is called quasi-periodic, because it's not exactly periodic, but eventually can become very close to the let's say to the phase we saw at the beginning. Okay, so I want to introduce also that's an example of a conformally symplectic system. I would also like to introduce a conformally symplectic map, and I will do so by introducing a map from the system that I showed before. If I take the spin orbit problem and I take the average along the P2 resonance, I obtain basically a dissipated pendulum kind of equation, and by introducing a symplectic Euler method, numerical method, I obtain a map. And the map that I obtain is this map right here that I will be talking a lot about today, which is going to be called the dissipated standard map. So this is a map, it's conformal symplectic. If I take the pullback, I get lambda times the symplectic form. So therefore, the Jacobian of f is equal to lambda. If I take lambda equal to 1 and mu equal to 0, I get back the standard map. So that's why people call this dissipated standard map. I will be interested here mostly in the case where lambda is a number between 0 and 1. Lambda is a constant between 0 and 1. Then you have a dissipated system that contracts the symplectic form with array lambda. But also at the end I will talk a little bit about an expanding map. So I could allow lambda to be.
Okay, can you say one word what is physically mu? Because I
mu?
before.
Okay, mu is a drift parameter. It showed up. I'm going forward. For instance, there. Okay?
Oh.
So mu comes from what? In fact, it's going to come from the product of these two constants. Because you want a friction that is proportional to the velocity, but this is the relative velocity of the angle along the Keplerian orbit. So that's why, yes, that's why you have that drift. Okay, so I was here. Okay, so let me talk about this dissipated standard map. First, I start with the integral case when epsilon is equal to 0. When epsilon is equal to 0, I get this very simple map. And the dynamics of this map are basically on the whole cylinder except for a circle, you have contraction with a rate equal to lambda. On the circle, what you're going to have is you're going to have a circle dynamic, okay, with rotation number equal to omega that depends on the parameters of the dissipated standard map. If omega happens to be a rational number, p over q, where p and q are integers, then the dynamic on the circle are going to be periodic. If p over q is not, if omega is not rational, then the dynamic is going to be quasi-periodic, and that means that every single orbit is going to be dense on the whole circle. Okay, the periodic orbit will come back to the same point where it started. Okay, so so how do we treat the existence and the persistence of these quasi-periodic orbits? I will focus on this quasi-periodic orbit. So let me take omega, an irrational number, and I'm going to take k to be the parameterization of the circle. So k is a function that takes the angle theta onto the cylinder. So I will say that the map has an invariant circle if this invariance equation is satisfied. What does this invariance equation mean? If let's say I have here the graph of k, the invariant circle, or I have a circle, and what this equation is saying is that the dynamics on the circle are conjugated to the dynamics on the circle with rotation omega, this let's say rotation number, are conjugating the dynamics of the map f. So that is to say, if I have a point here, let's say f corresponding to some value of theta here, and then I have another point there, which is k evaluated at theta plus the rotation number. So on this side, I'm going to have that the dynamic of this number is going to go to that number. Of this point is going to go to that point. So I want that to correspond exactly to the dynamic of the map f. So now we're going to move a little bit so that it's f of k. Okay? So I can say that there is an invariant circle to this mapping if I have this conjugacy. So that invariance equation is going to be a centerpiece of the theory that I will present. Of course, that function k can have many properties, but in particular it has to be periodic so that it really went around in the cylinder. Okay, so let me present, for instance, what does it mean to have a Km theorem in the sense of well, using this technology of the invariance equation. So one way to obtain a Km theorem would be by starting from a graph k, an approximate graph of a circle, which I call Ka, and if the invariance equation evaluated at this Ka is not exactly 0, but it's a very small number, I would like to implement a Newton method in Banach spaces so that I converge back to a time-exact solution. So that would be a Km theorem. In order to have a Km theorem of this kind, I have to start, or we have to start from an irrational number that is not only irrational, but it's an irrational number that's very hard to approximate by rational vectors. Okay, so that's the condition that I have here. Those numbers are from Diophantine. If you have trouble understanding this definition right here, you can think of d equal to 1, but you have an irrational number here. If you have an irrational number, this inequality tells you that omega cannot be very close to n over k, unless k is a really huge number, unless the denominator is very large. Okay. So, of course, you can obtain such a theorem if you have some non-degeneracy conditions. Okay, you have some non-degeneracy conditions that deal with the fact that you can move parameters to adjust. For instance, that's related to the parameter mu that showed up before. So, if you have that ability to move mu in order to adjust the rotation number, and introducing space of analytic functions, which are standard spaces in Km theory. So the fact is that in Km theory you use spaces that are defined not on the torus itself, but on a band that is around the torus. Okay, so then you obtain such a theorem. So what is the theorem? You start with a Diophantine number, and you start with an approximate solution that makes this quantity small enough. Okay, so the approximate solution has to be in a space, one of these spaces with regularity rho. And I'm stating first the theorem for lambda different from 1, but later I will relax this. I will relax this assumption. Of course, what are the conditions? You need the approximate solution to be good enough. So that is, you need this error to be very small, and very small corresponding to this quantity that involves the constants of the Diophantine number, but also other expressions that are computable with respect to the approximate solution. So you can say that if this error is small enough, you implement a Newton's method in Banach spaces, and that method is convergent, so you obtain an exact solution. That is a solution in a space of less regularity that satisfies the invariance equation exactly, okay? And that is close to the approximate solution that you started with, and close with respect to the size of the initial error.
So what is capital lambda?
Capital lambda is just a region of the parameter, so you want that to be a standard region, so that you still can move the parameter and still have solutions.
So you have to move the parameter because you choose omega.
You have to move the parameter because you're fixing omega at the beginning, and then you're gonna keep this omega fixed throughout the whole throughout the whole iteration. Let's say. Okay, so and well, let me just mention this briefly. As you can define the spaces in analytic functions, we also included in one of these papers spaces of smooth regularity, which was important at some point in K-Leon theory, but we also included them because these spaces happen to be very very effective and very useful for numerical computations that I will introduce later. But you obtain a similar kind of theorem. I mean, you start with an approximate solution, you make this iterative scheme, making some smoothing, and then you obtain a solution that is less regular, but it's still a tau. Oh, tau is okay. Let me show you. Tau is one of the constants of the Diophantine number. Yes. So let me show it everybody to remember. It's our notation, and then we're used to it, and then maybe people do not see it right away. Okay. So these are the kind of theorems that we obtain. These theorems have many consequences, of course. The key fact of these theorems is that you do not start from the integral case. You only start from an approximate solution, and this approximate solution can be obtained in many ways. It could be the result of a numerical computation. It could be an instant series expansion, or something else. In that sense, these a posteriori theorem are very good for validating numerical computations. If you have a computation and the computation is accurate enough, you can use the theorem in order to be sure that there's going to be a real solution nearby. Okay, and of course, the reason why is that true is that well, this theorem allows continuation of solutions. Whenever you have a solution, you know by the theorem that there's going to be a small branch of solutions nearby, so you can really follow this branch either numerically or analytically by using this theorem. And also this technology of the parameterization also, provides results like local uniqueness and bootstrap regularity. So you have solutions that are very regular. I mean, in the case of analytic spaces, they're actually analytic and they're unique. And we use these results in order to derive, for instance, criteria of the breakdown of solutions, because we're actually going to use this theorem in many cases to explore the boundary of analyticity, breakdown of analyticity of these quasi-periodic solutions. Okay, so something else that is very useful is that the proof of these theorems, the Newton method, is solved by using geometric identities, and these geometric identities, of course, depend on the fact that you have a symplectic structure. So the maps are not just dissipated maps in general, for instance, or the flows are not dissipated flows in general, but they satisfy some geometrical properties. Through these geometrical properties, you have geometric identities that you can use to reduce the Newton method. And what you obtain at the end is that the Newton's equations only include shifting functions, multiplying functions, differentiating, and solving cohomology equations with constant coefficients. All of those operations are very convenient to get estimates, and of course that's the way you prove the convergence of the theorem. But something else is that all of these operations are very easily implementable using the computer. So in the end, what happens is that you can implement this, transform the proof of the theorem into a numerical method, and the method that you obtain is very fast. If you use the fast Fourier transform, you obtain a method that is actually order of n log n operations, where n is the number of points that you use to discretize the invariant torus, let's say. Okay, so something else that is important is that these reductions work in any dimension because they depend on the symplectic form. That would be, so the geometry is the same in any dimension. And the fact is that the Newton equation that would be in principle not straightforward to solve can be transformed in sets of equations that are constant coefficient, that involve constant coefficient cohomology equations, and that can be solved. For instance, if you solve these cohomology equations numerically, you can use fast Fourier transform, and that's how you obtain methods that are order of n log n operations. Of course, something that I mentioned briefly when I introduced the theorem, and I will come back to that a little bit here, is that, so the theorems, so when you write down these equations, basically you can solve the equations when lambda is different from 1, which would be the symplectic case, but also when lambda is equal to 1, you can solve these kind of equations. So in fact, the way you could write the theorem, or the way we wrote the theorem, is in fact uniformly going through lambda equal to 1, going through the symplectic case. So that's just a part of the theorem. And of course, I'm saying everything here for the case of maps because the geometry is very let's say convenient to explain. But everything that I say here is analogous to the case of flows. In fact, I will present when I present numerical examples, I will present also a numerical example for the case of flows. So I was saying that we use these theorems and all these implementation, let's say, of the theorems or these numerical consequences in order to explore what happens to this smooth Km tori as the analyticity breaks down. Of course, so why does this happen? Because as I showed, there's many cases. I mean, starting from the integral case, you have a branch of smooth analytic even tori, and at some point this analyticity is lost. There is a boundary, and on the other side of the boundary you have examples of let's say orbits that do not correspond to invariant tori, and that's related to Aubrey matter theory, and of course the recent work of Alfonso and Stefano Marò. So this transition is called actually the breakdown of analyticity transition, and one is interested in describing the boundary between these two cases and saying something about this, something about the properties of this invariant tori as close as you can to the boundary. Okay, so this is what I was describing below. This great region. Let's say we could think of the region where you have invariant tori that are analytic, and outside here, that's the realm of let's say Aubrey matter theory, where you have you still have some orbits, but the orbits do not correspond to these Lagrangian manifolds. So I'm interested in actually describing or saying something about this boundary between the gray region and the blue region. So what blue region? The gray region and the white region. So how can you use the theorem? Well, you can use the theorem here because basically if you start a continuation, I said the theorem already suggests that there's branches that you could follow. So let's say you follow a branch of solutions, analytic solutions, and monitor these analytic solutions or the properties of these analytic solutions as you approach the boundary. So what happens is that if you, during the whole continuation, you can control the non-degeneracy of the problem, because that's basically fixed condition. And you also have results about regularity. So the branch that you get keeps being regular. And what happens when you reach the boundary? When you reach the boundary, you realize that something has to break down. And what happens, and that's what I was showing the result for solid spaces. So what happens is that at the boundary, the solid norm of the invariant tori are going to blow up. They're going to do so with some really fixed exponents that are related to the renormalization group operators, and you can use that. You can use these facts in order to explore or describe the boundary of analyticity breakdown. Of course, I mean this is just really a dummy slide. I mean, this is just repeating what I just said, that you can follow the solutions along the whole branch. You could compute them numerically and monitor the properties of the solutions, and then you can be sure, because we have this rigorously justified method, that when the subleft norm blows up, or in the case of the computer, the subleft norm is large enough and is blowing up with a certain exponent, you can be sure that you're at the boundary.
This scenario seems very similar to the case of no dissipation. Is there some difference?
There is actually no difference with the case of no dissipation, because the essence of the theorems, the posterior theorems, are exactly the same. Yes, yes.
It's uniform model bound.
Yes. It's exactly the same setting. Yeah. So actually, we didn't have to prove anything else. We already had the result for symplectic case, and then the abstract theorems already apply for the posterior theorems that we have for this case. Okay, so something else that is, so that's a criterion of breakdown related to subleft norms. Subleft norms blow up. There are other criteria for breakdown. For instance, Green's method doesn't use properties of the invariant tori. It rather uses properties of the linearization of periodic orbits with rotation numbers approximating the frequencies of the invariant tori, and of course the linearization properties. As the linearization properties of the periodic orbits changed, then Green observed in 79 that is related to when the tori disappear and disappear or are present. So together with Alessandra, Corrado, and Rafael, we introduced a Green's method for the case of conformally symplectic system. In the case of conformally symplectic systems, the situation is very similar also to the case of symplectic system, because you also have properties of the periodic orbits approximating the invariant tori that have the spectrum changes in some case that is similar to the case of the symplectic system. So that was already something that we realized. Of course, the properties of the periodic orbits satisfy some rigidity conditions. But let me just mention this. I wanted to mention this because Corrado is here as well. But let me go to numerical examples. Okay, so I go back to this standard map, which is very easy to handle, and it's very easy to do computations with this. So start with the standard map, and then introduce this parameterization. You have this parameterization of an invariant circle K here, and you start with an approximate solution, and you want to implement a Newton method numerically. so that you obtain the closest you can get to a real solution. So you want to make this error small. When you write down Newton's equations, you obtain equations of this sort, which involve difference equations with non-constant coefficients, okay? Which are typically you are able to solve them, for instance, numerically by using the order of n cubed operations. But by using these geometrical identities, you can reduce those Newton's step equations into these simpler equations. So the thing is that when you use the geometrical identities, you obtain two sets of equations that are decoupled, and each one of them involves difference equations with constant coefficients. Those equations are very suitable for solving using fast Fourier transform, and that's why you get methods that are order of n log n operations, which is the expense of applying a fast Fourier transform. So basically, what you can do is start from the interval case and then continue these invariant circles in the case of the discrete standard map. Here we did it for the case of the golden mean. You can do it basically for any rational number, let's say novel or not novel that you like. You do the continuation and you try to get as close to the breakdown as you can. When you get close to the breakdown, the invariant circle looks like that. But when you look at this conjugacy function that's conjugating, which is the part of the invariance equation that's conjugating the rotational dynamics into a rigid rotation, exhibits some subsimilar behaviors here along the graph, and that's related to, that is also related to renormalization theory, but that's also related to the scaling exponents that you observe as the sublet norm blows up. And so that's done in the case of a map. For instance, why not doing it in the case of flows? For the case of flows, there is a paper by Alessandra and Vergata from 2009 where they address directly some kind of equations like the spin orbit problem equations. So there's a similar treatment of these equations because you can reparameterize the angle x by a conjugacy function, but then the conjugacy function satisfies a PDE, okay, which is this PDE right here. So solutions of this PDE for you correspond to invariant tori of this spin orbit problem. What's the solutions? So how do they, Alessandra and Vergata solve it? Well, basically they implement a Nash Moser type method, which is in some sense similar to what we implemented here. But it's not related in geometry, but related in other types of cancellations. But the thing is that that theorem is also implementable numerically, following the proof of Alessandra and Luigi. And so some time ago, actually, I also did the implementation of that theorem, and you are able to do the same thing. You can continue this invariant tori all the way to you reach the limitations of the computer, and then you show solutions of this kind. Now, my master student Nicolas Gonzalez is taking these computations and really extending them into some really nice things. He's a very good programmer, and then he's doing very, very nice implementations. So that's something that's on the go. But what you observe is exactly the same. As you do the continuation of this tori, you approach some point, you monitor the sublet norm, and then the sublet norm blows up with exponents that are related also to the renormalization group of that case in particular. And then what I'm showing here is, it's very hard to see, but that's the Fourier spectrum. So you observe that the Fourier spectrum also has some patterns that are related also to the emergence of these self-similar behaviors in the conjugacy of the function. Okay, so that's something that you could implement numerically using these sublet methods. But regarding the geometry of these invariant circles, here I have an invariant circle that's very close to its breakdown. Here the computation involves millions of coefficients, and then you can see that the computation, as in the case of the spin-orbit problem, develops some patterns, right? And then people have explored those patterns. But there was the question that was asked to me by Jordi Lluís Figueras was, of course, this is a quasi-periodic attractor, right? So in particular, it's a normally hyperbolic invariant manifold. It has a stable bundle whose contraction rate is equal to lambda. Okay, lambda here is equal to 0.4, and it has a tangent bundle that's equal to the ratio is equal to 1. Okay, so if it's an invariant, if it's a normally hyperbolic invariant manifold, then you have initial theory. So how is it possible? What happens to this manifold as you approach the breakdown? Okay, so when you approach the breakdown, you still have the theory of normally hyperbolic invariant manifolds that tell you that the manifold is going to persist as soon as it is hyperbolic, and this manifold is always hyperbolic because the rate of the stable bundle is always equal to lambda. So then we decided to do a computation with this kind of setting. So you have a invariant circle there, you have the stable bundle in red and the tangent bundle in blue, and by this parameterization method you're able to write parameterizations of these invariant bundles. Okay, so the parameterizations of these invariant bundles are given by that, and then you get that also by the geometric properties of the system. So this is the game we started to play. We did the computation of the invariant circle. For instance, here I show some point of the computation for some epsilon equal to 0.5 for the dissipating standard map. And what I'm doing is I'm plotting the angle, well, red alpha is the angle of every point along the invariant circle, and the blue alpha, every point along the invariant circle of the stable bundle, and the blue alpha is every point, well, every angle along every point of the invariant circle of the tangent bundle. Okay? So what happens when you perform the computation? Here, let me start. I mean, this is just a movie of the computation that we did a number of years ago, and then see what happens to the angles as we evolve. So the angles start moving as the circle starts deforming, and when you approach the breakdown of analyticity, what you observe is that was maybe not very easy to see, but as far as you can see with the computation, the angles become very close as you approach the breakdown of analyticity. So I will show the last point of the computation here. Okay, this is as far as you can go. I mean, this was done with millions of Fourier coefficients, and what you see is that there are points on these, well, let's say these two circles, where the red line and the blue line are extremely close. I mean, of course, what can you expect? You expect that at the breakdown of analyticity, the bundles are going to collide in points, and since you have rotational invariance here, the two bundles are really going to collide in a dense number of points along the angle theta. Okay, this corresponds to a strange non-chaotic attractor, and that's the way the bundles collide also shows scaling laws. Actually, in this case, the scaling laws happen to be linear, and this was already observed in other kinds of cases for hyperbolic cocycles by Aro de la Llave, Lluís Figueras, Marta Canadei, Masha Safirina, and Christian Berthold. So this seems to be something a little bit, I mean, that is in the universal side of things, because all of these many examples show these linear scalings. Okay, so let me talk about something a little bit different, which is related not to the, well, this is not related to the breakdown of analyticity, but this is related to other things well, it's related to the small dissipative limit. Okay, many examples in celestial mechanics, like the examples that the spin orbit model is a model for. You observe that the dissipations are extremely small. For instance, epsilon, which is related to the moments of inertia of the planet that's going around the period, is a lot larger than the dissipative exponent. So it makes sense for these kind of models to explore the limit of small dissipations.
These are numbers that are realistic for planets?
Yes. I got this from a paper by Alessandra. These numbers are for the moon. Yeah. So that's, but I mean, numbers like this you observe in many planets that have been observed.
For the moon, epsilon is 10 to the minus 4.
Or is it Mars?
Mercury, small Mercury.
Mercury.
No, even Mercury is 10 to the minus 4. So, an asteroid, a great asteroid. One of the 10 to the minus 2 is large.
Okay.
But 10 to the minus 4 and 10 to the minus 8 is something which
maybe that's typo. Yeah. It's 10 to the minus 4 and 10 to the minus 8. In any case, it is clear that these numbers are orders of magnitude smaller than the other parameters. Okay. So let's study the limit of small dissipation in a very simple system. I take again the standard map, and how do I introduce a parameter that makes that is good for studying the limit of small dissipation? For instance, I could introduce that now the conformal factor is a function of this parameter, let's say epsilon, and when epsilon is equal to 0, the conformal parameter passes through the symplectic case, and also the drift passes through the drift equal to 0. Okay, so that's a model you could study. So last year we started developing theory to study this limit of small dissipation as the dissipation tends to 0. Okay, the problem with this kind of models is that introducing this kind of parameters is a very singular perturbation. So what could you expect to do? So something that you could do is use this kind of singular perturbation techniques involving Borel transforms and resummation techniques that were done by many people, some of them in Rome. The problem is that in many cases, I mean, in order to perform resummation, you need to have domains of analyticity that involve that at the singular value, which is epsilon equal to 0, you can include a ball that is tangent to the imaginary axis. And in many cases, as I will explain briefly, you don't have that case. In many cases, you have domains that look like that, where it's impossible to include a ball that is tangent to the imaginary axis, because it seems to be that you need to remove lines that pass through the origin with some inclination, let's say. In fact, that's exactly what I'm saying is described there. You need to remove balls that have radii that are decreasing faster than any power, and have centers along lines that pass through the origin. So this is not a very good setting for using resummation, because you don't have an Nemalina-Sokal theory. So going back to these conformally symplectic systems, so you have basically the same geometrical setting. Now the systems satisfy those geometrical identities, but the conformal factors go through the symplectic case as a parameter vanishes. Okay, so in general, you could think that this conformal factor is a function that can be very close to epsilon equal to 0, has expression like that, and the question is how to state a posteriori term in the same sense, using parameterization methods and using a posteriori techniques. So you do we do it the same way. You fixed a rotation number omega that has to be Diophantine, but in this case you need control over how Diophantine is frequency in terms of okay, this is a straightforward in terms of this constant nu that shows up here. And that's going to be important because of the quantitative theorem that I'm about to show here. So that writing the Diophantine condition in this way allows you to have control on how big these constants nu are. And then you can also define the this expression down here, which also involves the relation between the Diophantine number omega and the conformal factor lambda, which is going to show up actually in the listed series expansion. So if you have good control of those two quantities, then you have a Diophantine number. I'm sorry?
That was yeah, that one.
This one.
This one, yes. But I don't understand because one is a complex number, the other one is a real number. So
yes, it has to do. This has to do with the cohomology equations. So when you use the geometric identities, you separate the Newton's equation in two cohomology equations. One of them has constant equal to 1 in front. The other one has a constant equal to lambda. So you can solve those cohomology equations when these things are controlled, and that's precisely what shows in Fourier space. Let's say. Okay, so same flavor for the theorems. You start from an approximate solution. You have an approximate solution K that satisfies the invariance equation approximately, and you have non-deterrence conditions that are also going in the same direction as the a posteriori theorem that I presented before. And well, you can basically mimic the proof of the theorem that I presented before, but you get a quantitative a posteriori theorem. And we say that it's a quantitative posteriori theorem because you make it explicit that these quantities that I just defined show up in the smallness of the error right there. But the conclusion of the theorem is the same. So you have you can get an exact solution. The exact solution is close to the approximate solution with respect to the same kind of quantities. And how can you use this theorem in order to say something about the domains where these tori are analytic with respect to the small parameter epsilon? Well, you do that by defining listed series. So the listed series are you're going to be able to write listed series, but in domains that look like the domain that I showed before. And the fact is that when you're solving the listed series, these kind of terms are going to show up. I will just mention that briefly, but I hope it will be clear the flavor of what we're saying here. So if you have control over these kind of quantities, then you're able to define the listed series, either in the space of epsilon, the small parameter, or in the space of lambda, which is the complex number of the conformal factor. So these are the sets, the kind of sets that you obtain when you have control over these quantities. So this is what I was describing before. So this is the set that I showed before. This is a sequence of poles of decreasing radii, which decrease faster than any power, and whose centers lie along lines that pass through the origin. And
the numbers of poles or lines on the right is related to the exponent 3?
Yes.
Yes, that's the epsilon parameter, and this is lambda parameter.
This is the epsilon parameter, yes, and this is lambda. Yeah. So I mean, this is just if you put all these points through this relation, you get that. Okay. So let me just say, how can you use the quantitative theorem that I showed before in order to say something about this toroid. Well, you have this theorem about the existence of toroid, but existence also of listed series up to any order. You start with an approximate solution in a space of analytic functions, and then you have a non-degeneracy condition. So the theorem states that you can write down listed series up to any order that are solutions. I mean, being a listed series up to any order amounts to the partial sums solving this kind of estimates right here. So now you use the quantitative theorem that you had before, because with these estimates that you have here, you can use that as an approximate solution. You put it inside the theorem, and the theorem tells you, okay, there is a real solution for that point. And since you can do these listed series expansions in the sets, or I mean in the white region, so the complement of those the sets by removing the balls, then you have analytic solutions in the sets where you have removed the balls. So what happens is that when epsilon is close to epsilon equal to 0, you have analytic solutions that are analytic almost everywhere. They're analytic in sets where you have removed a sequence of balls that are very small and that pass through, that have centers along lines that pass through the origin. So they satisfy the invariance equation exactly, and of course, the invariance equation are close to the approximate solution in the same sense, because you're using the same kind of theorem. Okay, so I mean, this is kind of the last thing that I'm going to say.
With these balls, I mean, really there is no solution, or it's just that the method doesn't work?
Well, the method doesn't work. So it's not clear what is the optimal set. It is not clear what is the optimal set when you have analytic solutions. But in these sets, we can produce solutions. Okay? So we conjecture that actually the optimal solutions are contained. The optimal solution is contained in the set that we present. But I mean, we conjecture that the set is very close to optimal. So maybe it misses by a little bit, but not a lot. And so this is what I'm stating here. So I describe a little bit the sets. Okay, so you have the sets where you remove the sequence of balls along lines, and the radii increase very fast. And what the conjecture is that this is very, very close to optimal. So the true set, and this is something that might not be very easy to prove, but I think it could be a very good result. Is that what is the optimal set? I think it's a very good question. But something that we're able to show is that this, of course, the boundary of these sets is very thin, but there is no monodromy. So you're able to continue. You're able to continue this invariantorial with respect to epsilon through the boundary of the set, and you don't get branches of different solutions as you go through. So let me just show very quickly some numerical work done by Adrian Bustamante, who was my master student and who's now a PhD student at Georgia Tech. So basically, Adrian implemented this listed series expansion with, ridiculous precision using the thousands of digits, or 1,000 digits, and then computing the poles of this listed series expansion and plotting where this poles. So it turns out that the poles seem to be in places where we predicted that the set was not going to be, there were not going to be analytic solutions. So, and something else that Adrian did is that he did numerical continuation and verified that there was no monodromy when you go around these poles, and so that was so this is work that we're finishing. So just to finish, let's say some things that I mentioned here. I showed some numerical evidence that gives a motivation for proving very good numerical results, and they're all based on many things, on listed series, on analysis, on tangent theory, and a little bit of geometry. So this is contained in a series of papers that you could find in my webpage, and I thank you very much for your attention. Thank you.
Thanks, Renato. So, questions? We already have some questions, so if not, I will take the opportunity to ask you one question, which is related to your work with Giardini Figueras.
Yes.
Where you show the collision of the invariant bundles, the center and stable bundles. Can you do the same in the more dimensional case? For example, if you take the Fréchet map?
Yes. So the more dimensional case is kind of delicate. So the thing is that in one dimension you have results relating the conjugacy function into the ridge rotation. In more dimension, this is not trivial, and you use the fact that you have you have a conjugacy, and if you have a conjugacy that relates that is a ridge rotation into the invariant torus, then you know that this conjugacy has some regularity. In higher dimension, this is not the case, because the conjugacy can could develop singularities along the torus that you don't really see. So for that case, it is not true in general in higher dimensions, but there might be cases where you do have this regularity, and you do need the regularity in order to compute the invariant torus. So yeah, so it depends on that.
Yeah.
Yes.
And the second question is related to the figure that you showed with Bustamante.
Yes.
The singularities which go very well along these lines.
Yes.
These are obtained by using Padé approximates?
Yes. So yeah, so basically you write down the listed series up to a very high order. So that you want to compute the poles of that function, and you use Padé approximates, and that's why you need precisions that are very high, because these Padé approximates have very bad condition numbers. So you need so yeah, in the end, the last computation we used 1,000 digits. So.
What is the order of the Padé approximates?
The order of the Padé approximates, we used several examples. For this computation, it was 1,000.
1,000.
1,000 terms in the listed series, and each term has 1,000 digits.
So when you say 1,000 digits, 1,000 digits, you say around 1,000 or 10,000?
Well,
which program is
we
implemented?
did it in Pari.
In Pari.
Yeah, Pari.
With
so it was
any number of digits.
Well, it was around 1,000. Probably the highest number of digits that we used was 1,100. 1,100.
Okay.
Yes. But that computation already took several weeks.
Yeah, I understand.
Yes. So it's
More questions? So if not, let us thank Renato again. And we invite all of you to join us to have a coffee break. In the common room. Ciao.